Okay, today I want to deal with the last major topic before we do the quiz on Lewis structures. With Lewis structures, we've been talking a lot about the octet rule, where every element has to have 8 electrons in its valence shell, 8 dots surrounding it, all that good stuff. But of course, there's always exceptions. So today we're going to look at exceptions to the octet rule. The book has, the PowerPoint from the book has 2 slides on this, where they show the odd electron atoms, incomplete octets, and expanded octets. Oops, there it is. As usual, I hate what they do, so I'm going to show it to you my way. So, let's look at the 3 major exceptions to where the octet rule doesn't work. The first of them is something called an incomplete octet. Octet means 8 electrons. Incomplete means you don't have 8. You have fewer than 8. That generally happens with electron deficient molecules, where the central atom is from the second column, like beryllium, or from the third column, often boron or aluminum, where you don't have enough electrons to go around. And so you can't make an octet. In some cases, you can make the octet, but it's better not to. So let's take a look. The examples I give here are beryllium hydride and boron trifluoride. Let me come to my whiteboard here, and we'll draw beryllium hydride first. So you got Be in the middle, attached to 2 hydrogens. Now, beryllium has an s2 configuration, so that's 2 electrons coming from beryllium here. Each hydrogen has 1, that's 2 more electrons. Total of 4 electrons. Okay, so we're electron deficient. Let's make our bonds. 2, 4, we made all our bonds. The hydrogens are good, they only need 2. Beryllium needs more electrons, but we've used all our electrons. We only had 4 to work with, and they went into the bonds. So we come up short a lone pair here and a lone pair here on beryllium. Normally, in this case, of course, we'd make a double bond. But there's no lone pairs on the hydrogens to make double bonds either. We're electron deficient. And so the molecule is stuck with this situation where there's not a complete octet on beryllium. Molecule exists, so I guess it's allowed to do that, but it's not optimal, obviously. But yeah, so that's an example of an incomplete octet. If we looked at boron hydride, BH3, which I'll show you here, I guess. Similar situation comes up. Boron has 3 electrons, 4, 5, 6. So 2, 4, 6, there's your molecule, and that's all you got. There's no electrons to have lone pairs, so again, boron is stuck with the incomplete octet here. Notice the central atom is the one that gets the incomplete octet. In this case, it's hydrogens, they can't. But now let's look at boron trifluoride, because there's a situation where you could make an octet, but it chooses not to. So now you got boron in the middle, surrounded by fluorines. So each fluorine brings 7 times 3 is 21, plus 3 more for boron, S2P1, gives you 26, right? Yeah. Wait, 7 of this 21, 24 electrons, sorry. You got 24 electrons to work with. 2, 4, 6. All right, great. We use 6 of them. 8, 10, 12. We got our lone pairs there. 14, 16, 18. Got our lone pairs there. It's hard to see them. 20, 22, 24. We got all our lone pairs there. Okay, great. So we used all our electrons. Fluorines all got lone pairs. Boron only has 2, 4, 6 electrons. It comes up short. Turns out the molecule actually leaves it at this and does not form a full octet. Notice you really could, if you wanted to, form an octet here. You could take, I'm going to redraw it quickly. Lone pairs. I could take the lone pair from right here and shift it into a double bond. And that would give me 2, 4, 6, 8 on the boron. It would give me a full octet. 2, 4, you can't see that electron there, 6, 8. Fluorine has an octet. These fluorines already had a full octet, remember. So you could make a full octet here, but the molecule chooses not to. And here's the reason why. Let's look at formal charges. The fluorines with single bonds, 2, 4, 6, 8, well, 7, you got to break that. So 7 electrons. They came in with 7, they're good. Same for that fluorine, has 7 electrons. This fluorine, 1, 2, 3, 4, 5, 6, is short electrons, so it has a positive formal charge on it. The boron, 1, 2, 3, 4, one for each bond, remember, came in with 3. It has a negative formal charge on it. Now, back here with the incomplete octet, 1, 2, 3, boron came with 3, it's got a full octet. And all the fluorines, I'm sorry, it has a 0 formal charge, I should say. All the fluorines have their 2, 4, 6, 7 electrons, so they all came with 7 also, and they're good. So the incomplete octet has no formal charges. Shifting to make a double bond, you get formal charges. That's less optimal, as we've decided back when we were first doing formal charges. Even worse, notice, we accomplished this full octet by forcing fluorine to have a positive formal charge. Remember that rule, the electronegative element should never get a positive formal charge. So fluorine, the best electronegativity of them all, well, geez, that's just not going to happen. Wimpy boron here taking electron density away from fluorine, not going to happen. And so here's a situation where the molecule could have formed a full octet, but it chose to stick with the incomplete octet so that it wouldn't have inappropriate formal charges. Now, we actually have evidence for this based on a reaction that actually happened. So let me come down here. I'm going to redraw my boron trifluoride again. I won't put in, I guess, all the lone pairs. But then now let's take that compound and allow it to react with ammonia. So ammonia, if you go through the Lewis structure, has a lone pair. I got to make my dots bigger, I guess. Has a lone pair on the nitrogen there. Now, boron trifluoride up here being electron deficient, having that incomplete octet on boron, yes, it's more stable than giving the positive charge to fluorine or something stupid, but it's still not the best situation in the world. So it's sitting there with this incomplete octet, and suddenly it bumps into this ammonia with that really, really tempting lone pair there. So the boron comes in, sits on that lone pair, and forms a bond out of it. And the two molecules form together into a new, bigger molecule with that bond. If boron had not had an incomplete octet, if it had done this structure over here with the double bond, there would be no empty bonding site, no empty site right here to latch onto that lone pair. And so this reaction wouldn't happen. The fact that the reaction does happen is an indicator that boron trifluoride really does do the incomplete octet with no formal charges, rather than doing the full octet with a formal charge. So that's incomplete octets. They happen again when you are electron deficient. Now, by the way, that bond that we just formed there, where one atom provided both electrons, the ammonia, the nitrogen provided both electrons, that's called a coordinate covalent bond. Not any different from any other covalent bond, but they give it a name. Now, another exception to the octet rule is something called a radical, or an odd electron molecule. These molecules have an odd number of electrons, so there's no way they can get a full octet. Consider nitrogen monoxide, NO. Nitrogen comes in with 5 electrons, oxygen has 6, that's 11 electrons, an odd number. There's no way you're going to get a full octet out of that. So, again, come to my whiteboard here. Oh, I ran out of room. So let's start a new file, don't need to save that. You got your N and your O, and we said we had 6 and 5 is 11 electrons. So 2, 4, 6, 8, 10, 11. Okay, so that's all we got. Now, nitrogen's really short electrons even down here. So we could take, say, this lone pair away, scribble it out, make a double bond. It's fine for oxygen, it still has 2, 4, 6, 8 electrons. Nitrogen has 2, 4, 6, 7 electrons. It's still short. Well, can we make another bond? No, that would put it over. So, unfortunately, we're going to have one that's an electron short no matter what because we have an odd number. The atom that gets shortchanged is the one with the lower electronegativity. Oxygen has a higher electronegativity here, so it gets the full octet. Nitrogen's lower electronegativity, it gets shortchanged. These molecules are called radicals because they tend to be very reactive because that lone electron wants to hook up with another electron somewhere. In particular, if I have another NO molecule nearby, the N from this one and the N with the neighbor can join up and form a bond, and they can double up. Those doubled up molecules are called dimers, and that tends to happen. By the way, in lab, when you produced NO2, if you'll recall that gas that could trigger asthma, and we kicked out the students who had asthma so they didn't have to breathe it, that gas actually does form a dimer, N2O4. That was also present in the air in the room. Not that it affected you any. Now, the last exception to the octet rule is something called an expanded octet, where you have more than 8 electrons on the central atom. That happens when you have electron-rich atoms. The sulfur hexafluoride, notice there's 6 fluorines around sulfur, so there's no choice but to have an expanded octet. The textbook shows you that structure right here. Notice there's 6 fluorines around the sulfur, 2, 4, 6, 8, 10, 12 electrons on sulfur. That's an expanded octet. It has more electrons than it should have. Now, how do you do that? You only are allowed S2P6, right? That's 8 electrons. Where are the other ones going? Well, don't forget there's d orbitals that we're not using. So those empty d orbitals that are waiting around to be filled later on the periodic table, if you have extra electrons, you can always shove them in there. Now, notice that means in order to do an expanded octet, you got to have a d orbital. So elements in the first row, hydrogen, helium, only have s's, no p's or d's. Elements in the second row have s's and p's, but no d's. So anything in the second row of the periodic table, you're not going to be able to do an expanded octet no matter what you try. The third period, yeah, you got your s's, p's, and there's that d orbital waiting to be filled later, so that can form expanded octets and anything beyond that on the periodic table. So notice sulfur is in the third period. It can do this, sulfur hexafluoride. Oxygen right above it on the periodic table behaves very similarly, but it can't make oxygen hexafluoride in a similar way. That compound can't exist because oxygen is up here in period 2 and doesn't have a d orbital to use. Okay? So I want to show you one example of a situation where it forms an expanded octet even though it wouldn't have. The example I gave on the PowerPoint I'm not going to use because it's going to take too long and I'm running low on time here. So let's use the phosphate ion. Oops, what did I do? Phosphorus surrounded by 4 oxygens. And it's a 3 negative ion. So you have 6 times 4 is 24, plus 5 is 31, 32, 33, 34 electrons to work with because of the 3 negative charge. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. No, wait, I definitely counted wrong. We should have enough electron. The electrons should be right here as it is. I'm not going to recount them because I'm low on time. But this is actually a valid structure for the phosphate ion. Oh, I skipped electrons down here. That's what happened, I guess. But whatever. If you count them all up and make sure I counted my 34 right, which I don't know, you have the right number of electrons here. But notice each oxygen, 2, 4, 6, 7, has a negative formal charge. And phosphorus, 1, 2, 3, 4, it came in with 5, it's got a positive formal charge. Now, we can reduce that by taking, say, a lone pair right here, forming a double bond. That makes the oxygen have 2, 4, 5, 6, makes the phosphorus have 5, its formal charge goes away. So by forming a double bond, you actually reduce the formal charges, but now you have an expanded octet on phosphorus. And I'm out of time. We'll talk again tomorrow.